So in this lecture, we are learning about the concept of gradient descents for linear regressions. Just we have seen in previous lecture how the gradient descents algorithm works, and it is just simply a iterative and programmatic algorithm. And just we are applying the in linear regressions the gradient descents and see how it works. And after that, we have see that it have some limitations and how to omit these limitations, how to handle these limitations. Okay, let's start. So just write down the linear regressions. In linear regressions, we have see that at the end of the day, we have find an optimization problem. What is our, that is our optimal W is equals to arc mean of our W, that is summation I is equals to 1 to n, that is n is here number of, let's write number of data in training set, and summation W yi minus W transpose xi. Okay, here simply here we are using obviating, here we are not using W naught because here not used W naught, not used here because we are here avoiding the intercept term. Simple for easy of our calculations, for easy of our calculation of mathematics, just here I am omitting the intercept term. That if you interested, just simply you are putting the W naught at simple calculate it, then you can easily this is the same thing, but easy of calculations I am not using W naught here, and simply here I am not using any regression term. Okay, here I am not using no regression term because of some easy of our calculations. So if you are interested, just put down the intercept term and regularizer term, just it is the same calculation it is here. Okay, just come step by step. So let's take this equation, let's take this, call these equations as a loss functions. For loss functions we call these equations L of W. Because why L of W we are calling here, just write down first and then I am discussing about. Equals to 1 to n yi minus W transpose xi a whole square. Here why I am using the L function of W, because we have already know the data of xi yi, because it is coming from our training data sets. We are only unknown about our weight vectors, because xi and yi is coming from D train. Okay, now to solve this equation, to find the minimum of these equations, we have to derivative it, we have to just differentiate it, but we see that W is a higher dimensional vector, so just we are using here the gradient concept, that over W of the function L, this one, and here we are using the simply I is equals to 1 to n. So first we have to derivative it. First just we am writing the derivative, then after finding the derivative we are compare it to 0 and solve it. So first write down the derivative term. So what, that's just simply square, we have to 2 into yi minus W transpose xi. Okay, after this term, so this term will be what, this term will be minus of xi. This is the simple derivative term of this. Now to solve these equations we are using the gradient descent. It's just simple, we are using the to find the to calculating that using the gradient descent, we are simply using the derivative of this function. So simply we are using these functions. So first let's write these equations one by one. So first we have to pick a random vector. Actually we have to calculate the minimum optimal value of W, so we have to first pick a random value of W. let's initially it is called w naught. It will be some d dimension. If the our vector belonging to d dimension, it will be some d dimensional vector. Let's call it is w1 w2. Let's call w01 w02 w03. Okay, so in second step what do we have to do? In second step we are calculating the w1. Similarly, just don't be confused it here. I am using simply it is w naught. Okay, minute. Here I am using, just take the medium one. w01 w02. Okay, so now we am going to calculate the w1 vector. So w1 vector will be what? w1 is equals to w naught minus some learning rate of this derivative that we calculated previously of this derivative. So this one, I is equals to 1 to n 2 of yi minus w transpose xi into minus xi. Okay, now using this same, I'm going to the next step using the same formula. w2 will be what? w1 minus r of the same learning rate 2 of just simple 2 of xi yi minus w transpose. Here what will be? This w is actually w naught. Okay, this w actually w naught, this w. Okay, because we are going to calculate the w1. So we are here using the w naught. Here what will use? Here we are using the w1 because we are going to calculate the value of w2. Here we are using the value of w xi. Okay, so we are just continuing this process after as time increases. So what we will find? We are first initially pick the random value w naught, then we are going to calculate it w1, then w2, add iteration increasing. Suppose let's take we are stopping our iterations at 8th iterations. So what will you calculate it? So when we'll stop it, I'm also, this concept is also previous, just I am repeating this concept again. When we'll stop these iterations, if we find that our differences of wk minus 1 and wk is a vector of very small values. Okay, is a vector of very small value. Okay, then we are going to we are stop this iteration and we declare that our optimal w will be what? Optimal w will be w star is equals to wk. Okay, then it will be our optimal w. Now the main problem is that just you see this equation, just I am writing this equations again in iterative way. Wi, so simple, here I am using wj equals to wj minus 1 minus r into summations of I is equals to 1 to n minus 2xi yi minus wj minus I, j minus 1 transpose into xi. This is the actually our gradient descent. This is actually our gradient descent equation. this equation actually our gradient descent equation. This is simple our gradient descent equations. But what is the problem here? So just to see this, if you see this if you just see these equations, so if you see these equations, so now what is the problem of this equation? So here n is what? Here actually n is what? Just change the color. Here n is the what? N is the number of data points in d train data. So in real scenario, n is very large, very large. N is a very large number. If you just simply in a common machine, a common data set, even real data set in a common data set, so n is something. Let's take n is 1 million data point. Okay, let's take m is 1 million data point. Then what will be our problem? So in every iterations we have to calculate it 1 million number of points. In every iterations, just see this 1 to n, we have to summing all the points. We have to sum all the points. So this is a large, this thing is a large, we need a huge amount of time and huge amount of resources to calculate its iterations. So this is actually a time taking matter and expensive matter, this one. This thing is the main problem. This is a actually, if n is very large number, if n is very large number, then the computing this summation is very expensive and time taking. Okay, just see, if our training data set is so large, actually if our number of data set is large, then to calculating these summations is very expensive and also time taking. Okay, so to reach w0 to w1 and w1 to w2 dot in each step, we actually need a huge amount of time to calculate this to this. We need we need we need it needs a huge amount of time, huge time. Okay, so if in each iterations we take huge time to total to convert this thing, it is actually in real world it is impossible. Okay, so to avoid this thing, we are using the gradient descent technique, sorry, stochastic descent technique, that we'll discuss in next lecture. So to avoid this thing, so one key hack, one most beautiful hack, as we call the most beautiful hack to remove this thing. So the most beautiful hack to remove it, call it as this technique called the stochastic gradient descent technique. Okay, so to see, just you see this problem, So if our n large data set is so large, actually in real world data is so large, there have many times 1 million, and it is a common matter in 1 million data set, and you see it is a 1 billion and billion of data sets that we have. But to calculate this sum, actually we have faced the main problem. So it actually takes a huge amount of time and very expensive to calculate these situations. So to avoid these situations, we are using the stochastic gradient descent technique. Okay, that we see in next lecture. Okay.